Q&A session series, Recurrent Neural Network, Part 3. In this video, we will see how to implement backpropagation in an RNN. When we implement backpropagation in RNN, we use a method called BPTT, which is an abbreviation of backpropagation through time. This video also explains various types of RNNs and how they are applied in real-world problems. First, let's see how to compute the loss function in RNNs. In RNNs, a loss function is computed for each block. The loss function of the first block is L1, that of the second block is L2, and so on. Then, the total loss will be computed by taking the arithmetic mean of each block's loss function. For example, we have this sequence data. These are actual values in each time step. And using this RNN model, we get these predicted values for each time step. Using the difference between the actual and predicted values, we can compute the loss function in each time step. And we can compute the total loss by taking the arithmetic mean of the loss in each time step. Next, let's see how RNNs learn to minimize the loss. Let's go back to the formula of a hidden layer in RNN. As with the case of ordinary artificial neural network, an RNN model learns the weights and biases that minimize the loss. That is, for this formula, the model learns the WH, WX, and B as parameters. However, these parameters are influenced by past information. So, in RNN model learning, we need to reflect the influence of past information. Therefore, in RNN model learning, a special type of backpropagation is used to consider past information. This method is called BPTT, backpropagation through time. Let's see the process of BPTT. In backpropagation, the updates of weights and biases are repeated many times to minimize the total loss. We can express the weight update by this equation. First, multiply the learning rate with the weight gradient. Then, subtract the product from the current weight. The weight gradient can be found as the partial derivative of the total loss with respect to the weight. We can express the loss at a particular time point in this way. We can rewrite this expression in this way. The pi represents a product of sequences. So here, it means that all fractions expressed in this way will be multiplied. The time of the denominator is t minus 1, so t starts from 2. Let's continue with the weight gradient. We know that a hidden layer can be expressed in this way. Take its derivative. It can be expressed in this way. Let's plug this into the expression of the weight gradient. By doing so, we can express the weight gradient by this equation. One of the weaknesses of a recurrent neural network is that it is likely to suffer the problem of vanishing gradient or exploding gradient when the data size is large. This is the expression of the weight gradient we saw in the previous slide. Let's focus on the hyperbolic tangent. The derivative of the hyperbolic tangent can be expressed in this way. It includes the square of the hyperbolic cosine. The hyperbolic cosine can be expressed in this way. When x is 0, the hyperbolic cosine is 1, and otherwise it is greater than 1. Thus, the derivative of the hyperbolic tangent is smaller than 1, unless x is 0. Since the derivative of the hyperbolic tangent is smaller than 1, the larger t becomes, the smaller the gradient will be. It means that the larger the data size is, the smaller the gradient will be. It is a problem of vanishing gradient. Because of the vanishing gradient problem, recurrent neural networks cannot learn from large-sized data. Recurrent neural network is likely to fall into the exploding gradient problem when the weight WH is very large. As we saw in the previous videos, a recurrent neural network has an input sequence fed into the input layer, and an output sequence comes out from the output layer. But we can use different types of recurrent neural networks depending on our task types. Specifically, we can change the sizes and types of input layers and output layers. In the following, we will see 4 types of recurrent neural networks: one-to-one, one-to-many, many-to-one, and many-to-many. One-to-one RNN is a basic type of neural network. We use it for general machine learning problems. It has a single input and a single output. Specifically, its input data and output data are fixed size vectors. In a one-to-many RNN, the input data is not a sequence, but the output is a sequence data. That is, a one-to-many RNN has a single input and multiple outputs. In other words, a one-to-many RNN generates multiple outputs from a single input. One-to-many RNNs are used for a problem where we want to generate sequenced output from a single input. A typical example is image captioning. In image captioning, we use an image as the input and output a phrase. An image is not a sequence, a single input. A phrase is a sequence, a multiple outputs. Many-to-one RNN uses multiple input to generate a single output. In other words, it uses a sequence as an input to generate a single element, a fixed size vector. This kind of RNN is used for sentiment analysis, where we predict sentiment scores from each text. Here, the text data is sequence, and the sentiment score is a number. Another example is a video classification, where the RNN uses movie data to output categories. A movie is a sequence of images, and a category is a single output. In a many-to-many RNN, both input and output are sequences. That is, it uses a sequence to generate a sequence. There are 2 types of many-to-many RNN. In one type, the input length equals the output length. In this architecture, the input and output correspondent with each other at each time step. We can use this type for video captioning. In another type, the input length is different from the output length. We can use this type of RNN for machine translation, where an input string can be longer or shorter than the output string. In this architecture, there is a time lag between the input and the output. For instance, in machine translation from English to Japanese, the recurrent neural network reads an English sentence first, then processes the sentence, and then translates it to Japanese. Now, we conclude the Q&A on recurrent neural networks. Next time, I will upload a video on machine learning as usual. After that, I will answer the questions I received about linear algebra. Thank you for watching. Please thumbs up and subscribe to my channel.